Okay, so this is lecture 21. Hard to believe that we've had that many so far this semester. Well, today we're going to talk about the scatterplate interferometer. The last class we started our discussion of the scatterplate, and I ended it with a question or a statement saying I didn't see how this scatterplate interferometer could work at all, but I know it does. So let's just say a few words about the scatterplate, and then we'll try to figure out why it does indeed work the way it does. So we had a source here, and we said the source could be about anything. The lens doesn't have to be good. The beam splitter doesn't have to be good. But this lens will image the source onto the mirror that we're testing. And we typically will use this for testing a concave mirror. We can use it for other surfaces, but it requires additional optics and loses some of its nice features. So this lens will image a source onto the mirror. We go back through the scatter plate, which I'll come back to, through our beam splitter, through another lens. It's not real good. And this lens will image the mirror we're testing onto the final interferogram plane. And so since the source was imaged onto the mirror, this lens will also image the source back here on the interferogram plane. And we said we really have four beams back here. We said we have a beam that is scattered the first time, and then the next time through goes directly through, and that was just going to be an image of the source right here, and that's a bright spot, and just a hot spot they often call it, and so we will forget about it. We'll see it in the final interferogram, but it's not going to bother us. Then we're going to have a beam that is scattered the first time and is scattered the second time through, and that's just going to kind of give a little mess here. It's going to reduce the contrast of the fringes a little bit, but when we look at the interferogram, we'll see it's still going to be excellent interferogram. Then we have a beam that goes directly through the first time, so it's focused onto the mirror, so it doesn't see any of the errors in the mirror at all. And then this comes back, it's scattered the second time, and that's going to end up being the reference beam. And the test beam is a beam that was scattered the first time, comes back here, goes directly through, and ends up back here, just imaging the mirror back here, and that will be the test beam. So we have the reference and the test beam, and it's going to give us fringes very similar to what we had with the Twyman green or with the laser-based Fizeau. So the question what a statement I was giving at the end of last class was that we're trying to measure small height variations on this mirror surface, little errors on the mirror surface. And we measure that by this beam that's scattered the first time through here and then goes directly back through the scatter plate the second time. We measure these height variations simply by, well, this beam will travel different distances depending on the height variations, and so there's going to be a small phase variation across this scattered direct beam. And from that phase variation, hopefully we're going to measure the mirror surface. But the thing is always, what used to be confusing to me, was that we think when a beam is scattered, there's all kinds of phase changes introduced, all kinds of random phase changes introduced. And how do we pick out these small phase changes due to the light traveling a little bit different distance, depending on the height variation on the mirror, from all these random phase changes due to the scattering process? Well, the secret here is that, the two beams we're interfering, one is scattered and then direct, and the second one is direct and then scattered. If some way we get the same random phase variations in both of these beams due to the scattering, so if we get the same random phase variations in both the test and the reference beam, they will subtract out, and we're going to be left only with these small variations due to the light traveling slightly different distances because of the surface errors here. So how do we get the same phase variations, same random phase variations in both the test and the reference beam. Well, that's where the inventor of this scatterplate interferometer, Jim Birch, was so clever. What he said was, let's see, so this beam comes along here, and it's scattered. You know, we'll trace a ray here. The beam is scattered there. Well, some phase change due to the scattering. I don't know what it is, but some phase change due to the scattering. And it comes over here and comes back through here again. The direct beam goes straight through here, and it comes back down here, and now it's scattered down here. So if I have the same phase change due to the scattering, the beam going through here the first time up here, that I have with the direct beam coming back down here, then both the test and the reference beam will have the same phase change due to scattering, and this random phase will drop out. So what he really wanted was that for every little scatter point up here on one side of the plate, he wants an identical scatter plate down here. Now, I said last class, this scatter plate, if you were to just look at it with your naked eye, it would look like a piece of ground glass. But if you look at this through a microscope, high enough magnification, for a good scatter plate, you'll see something like this. So I look at this region here. Oh, I have something down here. It's about the same. I look at this. Oh, about the same over there. Look at this. Oops. I look at this, and about the same there. So there's a point here about which I have inversion symmetry, or flip symmetry, whatever you wish to call it. And that's the secret of this scatter plate. That is how this scatter plate differs from a piece of ground glass. You have to have this inversion symmetry. And this is a true photograph of a scatter plate. This was one that was made for working at 10 microns. So these little scattering regions are larger than what you'd have for the visible light. In a little bit, I'll talk about how large these little scattering regions have to be. But, so this was made for 10 microns, so these scattering regions are larger. And so I could easily see this through the microscope. And I liked this picture so much that for a few years I used to have that on the door to my office, because I thought this was pretty neat. But that's the whole secret here. We have to some way make a scatter plate. We'll see how we do that later. But some way we're going to have to make a scatter plate that has this inversion symmetry. And then this random phase due to scattering will be the same in both the test beam and the reference beam. And since we're always finding the difference between these two beams, that will drop out, and we're simply left with the phase variation due to the errors on the mirror surface. So I think that is pretty clever, pretty cute. Now, it turns out, and we'll see a slide of this in just a second. Turns out, I want the scatter plate near the center of curvature here, so the mirror will image the scatter plate back on itself, but inverted. And it's going to turn out that if I move the scatter plate sideways, I will introduce tilt into the interference pattern. And if I move this longitudinally, I will introduce defocus into the interference pattern. So let's see if we can kind of see how that works. And as I said, Larry Rubin, who had done his a PhD dissertation on this, went through all the math describing all of this. But let's just see if we can see from a drawing how this works. So here's my scatter plate. And here's the mirror I'm testing. And as I said, this is at center of curvature. So this mirror will image this scatter plate back on itself, but inverted. So let's say the point about inversion symmetry is, is where this line is here. And so this is displaced sideways off the axis a little bit. Let's look at this scattering point. So I've moved the scatter plate sideways. So this scatter point is here. And the image of that is going to be down here. Okay? And as I move this sideways, as I move this up, that image will move down. Okay? But the corresponding scatter point to this is the same distance on this point, distance away from this point of inversion symmetry. So it's this, so that corresponding point would be down here. And as I move the scatter plate up, while the image of this point moves down, the corresponding scatter point on the other side of the scatter plate will move up. And so I'm getting a lateral displacement between the image of this point and the image of that point, and the corresponding point down here. And so that's like a little bit like Young's two-pinhole experiment. I have a little displacement between the points that are producing the light that's interfering, and so I will get straight equally spaced fringes. Now I just looked at one scatter point and a corresponding scatter point on the other side, and this scatter plate has a whole collection of these scatter points, but what I'm showing happens to one is the same thing that's going to happen to all the other ones. And so lo and behold, moving this sideways will introduce tilt. Okay? Now I said if I move this longitudinally, I'll introduce defocus. Okay, so let's say this is the center of curvature of the mirror, and this is my scatter point up there. And right now I'm going to have the scatter plate set up so the point of inversion symmetry is right on axis. But I move this inside of the center of curvature, and so the image of that is going to be outside the center of curvature. But the corresponding scatter point on the other side of the scatter plate is going to be right down there. And so there's a longitudinal displacement here. And so that's going to produce my circular fringes. Okay. So is that pretty clear then? Moving it sideways introduces tilt. Moving it longitudinally introduces defocus. And I showed this just for one single scatter point, but all the other scatter points are going to behave the same way. Okay? So what I want to do now is to show a photograph of a scatterplate interferometer. This is an old one. And I'm not sure who made this one, but I think, I don't know, Roland Shack or one of his students probably made it. The first time I saw a scatterplate interferometer was the very first time I visited optical sciences. I came out here, there was an OSA meeting in Tucson in about a long time ago, 1970, let's say, 70, 71. And I came out here to Tucson for the first time, and there was a tour of the building, and I saw, in our optic shop, I saw my first scatterplate interferometer, and I think this was probably it. And it was Roland Shack who was showing it off at that point. So here in this case, we're using a laser. Now, we don't have to use a laser. I'll show some results in a minute for using, well, maybe I'll show some for using other sources. Certainly, it's easy to make them scatterplate interferometers using almost any source you want. But so in this, there's a small beam coming out, and there's some optics here that will expand the beam up and then focus the beam down, and you can slide things back and forth to focus. You can slide a lens back and forth to focus a spot wherever you want, and so you're going to focus the light onto the mirror you're testing. And there's a beam splitter here, and then right here is the scatter plate, and you probably, you can't see it. It's just, it looks like a piece of ground glass anyway. And so the light would come out of the screen and to the mirror that we're testing. And then with the XYZ stage here, we would move this around to put this at the center or curvature of the mirror. Now, if I displace this too much from the center of curvature, I'm going to have too many, if I displace it sideways, I'm going to have too many interference fringes. I probably won't even see them. Or if I displace it too far longitudinally, same problem again. So we really want to put this point of inversion symmetry very close to the center of curvature of this mirror. So the scatter plate, it doesn't show it in this picture here, but there's always a crosshair or a dot or something that you can see with your naked eye showing where the center of the scatter plate is. And so when we put this in place here, we're going to want to look very closely, maybe a little magnifier, look very closely at both the scatter plate and the image of the scatter plate back on itself. And let's say we have a little spot at the center. And so first off, we want to get this longitudinally so the image of that spot is sharp back in the same plane as the scatter plate. So it's being imaged back on itself. And then we're going to displace this sideways just right so the spot on the scatter plate and the image of that spot falls right back on itself. And this is not too hard to do. We've had lots of students who have played with scatterplate interferometers, and they can align them pretty easily. And even I can align it pretty easily. I mean, it's pretty simple to do. As long as you have a mark showing where the center of the scatter plate is, so you can image that back on itself. If you didn't have that mark, I mean, you're lost. You don't know. You're just fumbling around here trying to get it in the right location. But if you have a spot at the center of curvature, you can just image it back on itself. Fine. It's easy to do. And so that's what we would do here. And then behind here, we would either have a camera or an eye, and we would see interferograms like this. I mean, these are 3 scatterplate interferograms for testing the same mirror, testing a parabolic mirror, concave parabolic mirror. And first off, what do we see? Well, I don't know how we can see from your seat, but you see some speckly pattern in here. And that's because we used a laser. If we used my flashlight or something like that, which I could use very easily, you won't see the speckle. But because of the coherence of the laser light, you'll see a little speckle pattern. You see this bright spot here. That's your direct beam, the so-called hot spot. And you see that in all 3 of these interferograms. But it's very localized, so it doesn't bother too much. Now we had a scattered beam, which I wanted to forget about. I said all it did was reduce the fringe contrast. And it does, but you see we still have pretty good fringe contrast, so we can't complain. And the difference between these 3 interferograms, I mean, it's for testing the same mirror. The only difference is that the scatter plate has been moved a little, in a transverse direction or in the longitudinal direction to change the amount of tilt or the amount of curvature. So as I said the last class, I mean, this thing is pretty common path here. And if I have vibration here, at least longitudinal vibration, well, it's going to do the same to the test and reference, essentially, so it won't bother me. And so I could easily set up this scatterplate interferometer on this bench that my computer is sitting on. And it would work fine. You might see a little motion of the fringes, and air turbulence will cause a little motion of the fringes too. But they're going to be pretty stable. And if I try to set up a Twyman green on this table, well, the fringes would really be jumping around a lot. So this will work in much more severe environments than a Twyman green. Any questions on this? Works? I mean, it works pretty well. Yes? The coherent noise? Well, we're getting that. The speckle here is the coherent noise. So how would I get rid of that? Well, first, I'd throw away my laser. I don't need a laser here at all. I could use almost any source, and it's going to work fine. Or if you insist on using a laser, if you focus the laser beam in the source, you focus it onto a piece of ground glass, and then you move this ground glass, and average. I mean, you move it fast, and you're going to average out the speckle pattern. And I think we'll see some of that in the next slide that I show you. So you can get rid of the speckle pretty easily. And if you don't use a laser, you don't have it to begin with. Yes?
So I was wondering if it's common that you want to make a scatter plate such that you have a good amount of transmission, so that there's not too strong of scattering, so that it's efficient?
Yeah, so the question is really how much scattering do you want? And if you have too little scattering, you're going to get a very bright hot spot. Because the direct beam will be very strong. If you have too much scattering, now you have trouble with a scattered beam is going to be too strong and the fringe contrast will be low. So you want, I mean, you end up with that, it's maybe 95% scattering or so. There's a wide range. It turns out it's not hard at all to make these scatter plates. You don't have to be too careful about the amount of scattering, but maybe 95% is a good number. And as I said, if you have too little scattering, the bright spot is too bright, too much scattering, the fringe contrast will be low because of the scattered beam. So these are old interferograms. I don't know who took these interferograms. Yes?
And you were also talking about how it's insensitive to vibration. That's the internal part of the interferometer. I mean, relative to the mirror, vibrations are still an issue, right? Like if you have the mirror on the table.
It's not so relative. The vibration really relative to the mirror is not so sensitive at all, because the reference beam is reflecting off of the mirror and the test beam is reflecting off the mirror. So just longitudinal motion here is not bad at all. Now if this is tipping, back and forth, that effect doesn't go away. But just a longitudinal motion, which is the biggest problem you have. I mean, I've seen this used many times where a Twyman green or laser base for ZO just has so much vibration that you have trouble getting data, while with this you can get data.
So you have a little fluctuation in tilt and focus.
Yeah.
That's not so...
No, I'm talking about this moving microns, not millimeters or something. Yeah.
Okay.
Yeah, you're right. As this moves back and forth, you're changing the curvature a little bit, but we're talking about micron motion, not a large motion. And I mean, you can have it sitting on a table, and you can hit the table, and it's still. I won't say the fringes don't move at all, but they don't move very much. It's pretty impressive, actually, to see how this is set up. And that's what the first time I saw one here at Optical Sciences. I mean, I had read about them in a book before, but I'd never had seen one before I saw one here. My first time I came to Optical Sciences, and there was a mirror way off someplace else, and the interferometer was sitting back here. There's no vibration isolation, and I just, oh man, this is fantastic. Fringes under conditions like this, lots of people around, walking around, not bothering you. So there's just a set of pictures that this student of mine who did his PhD on it, the first one who did his PhD on it, Larry Rubin did. And I guess all of these are lasers. And then some of these, he's doing a rotating ground glass. And so, I don't know, from your seat you probably can't see it, but the speckle really has gone away as you... so your source is the laser beam focused on the ground glass, and then that was rotating, and you're averaging out the speckle pattern, so it's not you don't see it. Unfortunately, I guess I don't have any pictures included here of just a tungsten source as opposed to a laser light source. Yes?
Is that a built-in physical mask for the bright spot in the interferometer?
The bright spot here?
It looks to me like there's a block for that.
No, well, this mirror had a hole in the center.
Oh, okay.
So that's what we're seeing. It's a central obscuration here.
Gotcha.
And then the source was focused right here. So that's where the hot spot is. And you can move that around. I mean, typically, you probably put it in the center. Well, there's a hole in the center, so I can't put it in the center. So you put it close to the center. But it's going to work fine if you put it out here. Just that there's going to be a little drop-off in a scattered light as you move away from where the source is focused. And so if I put this way over to the edge, I might see more drop-off here. In fact, right now, I mean, this is off to the left here, and probably there's a little drop-off in intensity over here on the right. Yes?
So unlike other interferometers, any coma you get...
You think what?
Any coma you see...
Oh, it works fine.
Is
You'll see it.
Surface, right?
Yeah. I'm going to show you one later where the coma doesn't appear. But, I mean, this measures all the aberrations. There's no... It's getting the coma. It's getting all the odd aberrations, wells even.
Sometimes misalignment, though, when you're testing, will give you coma.
Oh, yeah. Yeah, you could run into that problem if you misalign it too. But just moving the hotspot off axis, probably, it's not going to cause you a problem. This one, I don't know if you can see it, but this has many different wavelengths in it. And all the wavelengths are, you know, together here. And then as we move away from that hotspot, the different colors are separating a little bit. Even on the computer, it's a little hard to see that, but in practice you can see that they really do separate as you move away from there. In fact, there's a nice point. I'll say it from the next slide and then we'll come back. The OPD is 0 for the fringe passing through the hotspot. That is, a fringe passing through a hotspot, it's always a zero-order fringe. I mean, think about that. This is a very, very key thing here. So you always get a bright fringe where that hotspot is. Why is that? Well, if we think here for a second, I mean, this is where the hotspot is, where the source is imaged. But the scattered beam, for that point, the scattered beam's going right along the same path. And so, I mean, this is fantastic. The paths are exactly matched for here. And even if I have any phase change on reflection, it's going to be the same for both test and reference. And so this is a great feature that hot spot is always the zero-order fringe. It's always going to be a bright fringe. And so as we move away from that hot spot, as I go one bright fringe away, now the OPD between the test and the reference is always one wavelength. And if I move 10 fringes away, then it's going to be 10 wavelengths. And so that's why if I use a white light source here, if I have a lot of different wavelengths, you know, right around the hot spot, all these fringes for the different wavelengths are together. But as I move away from the hot spot, the fringes for the different wavelengths will separate and tend to wash out the fringes. But if I have just a few fringes here, I mean, I can use a white light source. In a second, I'll talk about how large the source can be too, but I can use a white light source here. Okay, so remember that, because this is I think a very important thing, that you always have a bright fringe where the hot spot is. That's always the zero-order fringe. Now, I've said that, and I don't want you to ever forget it, but let me show you something here. And this drove me crazy for years. If I look at these interferograms, the fringe that goes through the hot spot is a dark fringe. How can that be? I mean, it just can't be. It can't be. And I worried about that for years, I have to admit. So then I finally, used to be, if I had a problem and I couldn't solve it, what would I do? I would go talk to Roland Shack. So I went to Roland Shack. I showed him this. I said, this can't be right. You can't have a dark fringe going through the hot spot. And for one of the very few times in my life, I actually stumped him. Yeah, he couldn't. He said he had to think about it for a while. And it took him a few days, and then he came back with a possible explanation for this. I mean, we don't know who took these interferograms. They were taken here at Optical Sciences, quite sure, but we don't know who did it, don't know any of the history. His theory, the only way he could explain this was that this hot spot was really bright. And it was so bright that when the film, and this is back in the days of film, when the film was exposed, it actually burned a little hole in the film. And then this is a negative of that. And so that burned a hole in, so in the negative it looks bright, and the dark fringe that goes through here, because it's a negative, it actually was a bright fringe. So anyway, that's the only explanation he could think of. So I don't know if that's right or not. But this is, I mean, I've worried about that interferogram so much. But I mean, every time I've looked at it in real life, it's always, I mean, it has to be a bright fringe that goes through the hot spot. Now we're going to talk about doing some modifications and phase shifting and stuff that will change that. But just for the normal scatterplate interferometer we talked about, it's always a bright fringe where the hot spot is. So the next question might be, how big can the source be? And in Larry's dissertation, he has pages and pages of deriving this using the Van Sittert-Zernike theorem. And the final result is that the image of the source has to be smaller than the fringe spacing. And, you know, about 1/2 of fringe spacing is probably about the largest practical size. So let's look at a physical argument why that's true. I mean, his math showed it's true. But if we think here, I said before, the hot spot, you know, always have a bright fringe going through the hot spot. Well, if I have an extended source, I can think of that extended source as being made up of a bunch of point sources. And for each point source in the interferogram here, there's going to be a bright fringe going through that point source. But I run into trouble then if I put enough fringes in here so that the fringe spacing is comparable to the size of the source. Because for each point source it has a bright fringe going through it, but for the neighboring point source it may correspond to a dark fringe. And so it sort of makes sense that the image of the source in this interferogram has to be smaller than the fringe spacing, and something like a maximum size of 1/2 a fringe spacing is probably a good answer. So you understand physically why that sort of makes sense, and it really goes back to the point that I was emphasizing here at the beginning about the hot spot always has 0 order fringe going through it. And I guess I already said this down here that to get rid of the speckles, if we use a laser source, we would take the laser beam and focus it on a rotating piece of ground glass and average out the speckles. And if the scatter plate is too large, well, you're going to get some off-axis aberrations. That's maybe a little bit related to what you was asking a minute ago. And this is going to reduce the fringe contrast and cause error. And so the size, well, I mean, the real size of the scatter plate you can put up with depends upon how far away you are from the mirror, depends upon these angles here. What found kind of for normal testing, something like a 1/2 centimeter to a centimeter diameter is a typical size for a scatter plate. And if you're testing, small optics, small distances, you probably have to have a smaller scatter plate. Okay, and I guess if a scatter plate gets too small, and if you're using a laser source, the size of the speckles would become larger too. So do you want to know how to get a scatter plate? And if you're going to get one, I think you almost have to make one. I don't know anyone who sells scatter plates anymore. Years ago, Larry Rubin used to. And Edmund Optics, I think they bought some from Larry, and they used to sell them. But I don't know any place right now where you can buy a scatter plate. But the good news is it's fairly easy to make a scatter plate. And there's 2 ways. As I said, I had 2 students do their PhD on this, and they used 2 different ways of making a scatter plate. What Larry did was he took a piece of ground glass, just, regular piece of ground glass, and he illuminated it with a laser beam. And if you come over here some distance, what do you see? You see a speckle pattern. Okay? You've probably all seen that. And then he would record that speckle pattern. I think the original ones he recorded on film, and then he would bleach the film. I mean, you don't have to bleach a film. You can have a density scatter plate. But you get more light if you bleach it, so he would bleach the film. And then he went to photoresist. So he just made a recording on photoresist here and processed that, and that was a scatter plate. Well, he had to do one more thing. I forgot the second item, the most important item here. So he had the speckles here, and he recorded the speckles. But we have to have inversion symmetry. So how do we get inversion symmetry? And the easiest way is to just take this and rotate it 180 degrees and make a second exposure. Now, how close does it have to be to 180 degrees? And, I mean, you could go through some calculations, and it depends on the size of the scatter plate and so on. But if you can do this within an arc second, it's going to work. It's going to be great. That will give us the inversion symmetry we want. Now, maybe you think, I've told you before, I hate mechanical things, rotating something 180 degrees to within an arc second, to me sounds like money, okay? Because you have to have some fancy mount or something. But he just made a little fixture that had 3 little pins in it, and he put the photographic plate or photoresist plate on another little frame, and you set the frame in here, do exposure, and then just rotate that 180 degrees against the 3 pins, and it worked fine. It was quite simple to do. He did all the machining himself, and works very well. And I've told a number of people over the years how they might make scatter plates, and they really do. I mean, other people have done this. It works very well. Now, how big should the ground glass be when I'm illuminating it? And if I think here for a second, so I'm illuminating this ground glass, and I'm getting some speckles over here. And the size of these speckles is going to be determined by, well, it's determined by the wavelength, but it's determined by the maximum angle you can have between the 2 interfering beams, just like interference fringes. Speckles are nothing but complicated interference fringes. And so varying either the distance from the ground glass to the recording material or varying the size of the ground glass will vary this angle theta. And if I think here for a second, so that's determining the size of the speckles. And now when I take this material and I process it and later I illuminate it with a beam of light, the light that will be scattered out, well, I mean, this is sort of like a diffraction grating. And if that's the maximum angle between the 2 interfering beams, if I take this plate later and illuminate it with a beam of light, the angle between the 0 order and the 1st order will be about the same as this. And the angle between the 0 and the -1st will be about the same as this. So a majority of the scattering, well, a lot of the scattering, let's say it that way, a lot of the scattering, if I make this with an angle theta here, and I use the same wavelength in the reconstruction or illuminating this, the scatter will be spread over about 2 theta. Now that's not quite right, because you have higher orders too, and so it's going to be spread over more than that. But the majority of the light will be spread over something like 2 theta. And so when I make this scatter plate, I'd like to make it such that this 2 theta is about this angle. about the angle subtended by the mirror under test by the scatter plate. Now there's going to be light scattered outside of here because, you know, it's going to have higher orders and stuff. And, I mean, the amount of light scattered over here, it's going to vary too. The intensity is going to vary. But if you make it about, you know, make this about 2 theta, it's pretty good. Now you don't have to be real careful about that. If I have it scattering over more of an angle, well, it's probably more uniform over here, but I'm wasting some light. So it's kind of a trade-off between uniformity and wasting of light. If I make it too small, though, then I'm not doing a good job of illuminating the mirror. So, you know, something like 2 theta, but don't worry about it. I mean, just something close to that will be fine. Okay. So this, as I say, the theta determines the speckle size and then the scattering angle. So any questions on that? So you just take, you know, your recording material, photoresist, film, whatever, illuminate it with speckles, rotate it 180 degrees, make a second exposure, process that, and that's your scatter plate. One last thing you want to do, though, some way you have to determine where that point of inversion symmetry is. And what Larry used to do, he would look at it under a microscope, and he could play around a little bit, and then he would see the point of inversion symmetry, and he would just put a dot right there. And so it might take a few minutes to find that, but put the dot, and then in the future you always know where it is. And you could set up a system here where you automatically recorded a crosshair or something on it too, but he didn't do it that complicated way. And I keep referring to Larry as making these because he made hundreds of these, I guess, but I mean other students here have made them as well. So the second person, a student I had do his PhD on a scatter plate, was more of a computer person. And this came along several years later. And what he did was to calculate on the computer what the ideal scatter pattern would look like. So he could put in the size and stuff so he could get the scattering angle he wanted, whatever. And then he would send this, and he would record that data on the magnetic tape and ship that off to a company in California that had an electron beam recorder. And they would then use this E-beam recorder to record the computer-generated scatter plate pattern. So that worked out very well, too. Any questions?
How expensive does that process cost? This is and that's in...
the computer?
Yeah, okay, so they take a computer-generated pattern and they etch it in...
Well, computer, pattern, and then they would write it out just like they would in an integrated circuit, like they would electronics. And they just put it out on photoresist and then process the photoresist and send it back. They were like $1,000 a piece or so.
And processing the photoresist refers to a chemical etching?
Yeah, chemical etching. Mm-hmm. Yeah. I mean, I prefer the first method because it's cheaper, and a graduate student's doing all the work. But Michael preferred the second method for some reason. I don't know why it was. But,
make a more accurate...
Yeah, you could probably do a little more accurate. It's high, I mean, to get speckles as small down here, it was a little difficult, but they can do it. I mean, it's... Back when Larry did his original work, I mean, this was out of the question. They didn't have E-beam recorders that could make what we needed here. And I don't know, it's been 8 or 10 years since this was done. And, I mean, there's no problem now. But when Larry made these way back in the 70s, I guess probably late 70s when he did it.
What's the approximate scale of features?
We're talking about a few wavelengths of light. So if we're doing it for the visible, we might be talking about 3 microns, 2, 3, 4 microns. And for the one that I showed you the picture of, and this was at 10 microns, And so these were, I don't know, 20, 30 microns, something like that. In this one, what we did photoresist on germanium, and the student who did this was Osik Kwan, and then he etched through the photoresist into the germanium and then stripped away the photoresist. Oops. Okay. So this was invented by a man by the name of Jim Birch, who was a very, very clever guy. I got to know him in his later years. And he published this in Nature. And I have his entire paper here on the next slide. That's the entire paper he published. You note all the equations and all the figures and none, okay? It's only words. And I mean, I think I understand the scatterplate interferometer pretty well, but I tell you, I read what he wrote, and I can't understand it at all. I don't know. It was very, very opaque, and it's a kind of a strange paper, so short. But he knew what he was doing. That's for sure. He was a very, very nice guy. When in the early 80s, I spent one semester on sabbatical at the University of Rochester, and Jim Birch, who was in National Physical Laboratory in England, and I had visited him there once, but he was on sabbatical at Rochester the same time I was. So I got to know him fairly well then. Very nice guy. So the next step, next part I want to talk about is a phase shifting scatterplate interferometer. But before I do that, I have to tell you of a little experiment that maybe you've done this or maybe you haven't done it, but this is kind of nice. I mean, I love these fringes you get due to scattering, and you can often have white light fringes, and you know from what I've said before, I love white light fringes. So here's a little experiment that all of you can do. And so here is a rear surface mirror. Okay? So this could be the mirror in the bathroom. And you could, well, I mean, you could take a shower and get steam on the mirror, and that will do what I want it to do. Or if you want to do it here at Optical Sciences, you can take some chalk dust, if you can find any chalk dust anymore, and you could put that on this right here. So we're going to put something on this, say either, well, water that's condensed on here or chalk dust. And we're going to look in the mirror at ourselves. And I'm going to, you want a little light source that you put kind of here close to your eye. So we're looking in here and we're illuminating this. Now what is happening, you know, light goes through here, and when it hits this surface, some of the light's going to be scattered. I mean, most of the light's going to go straight through, but some of it will be scattered, it goes straight through. And so I'm going to form an image of that scattering surface back here. And when the light reflects off the mirror and comes back, some of the light's going to be scattered a second time through. So we have light scattered the first time through, we have light scattered the second time through, and there's a little longitudinal displacement here. And if I think here for a second, I mean, both of these beams, what's scattered the first time, what's scattered the second time, the paths are matched, so this is going to work with white light. And so I put this up here, and I'm going to see interference fringes. And what's going to be the shape of these fringes? Well, these two scattered patterns are longitudinally displaced if I look right straight down there. And so the fringes will be circular. if I move this off to the side, I'm going to see, circular fringes, I'm going to see away from the center of the fringes a little bit. But this is actually pretty easy to do, and you can, I don't know if I should encourage you to do it here at the university. Maybe the janitors won't like you putting chalk dust on the mirrors, but you can do it at home and just, take a shower and then try this, so it'll be all steamed up. And it works. I mean, it's pretty simple to get these fringes. It's kind of neat, and it's a lot like the Scatterplate Interferometer in some ways. Okay, so how can we do a phase shifting Scatterplate Interferometer? And first off, it's kind of difficult to do because both the test and the reference beams are going along the same path. So it's kind of hard to do the phase shifting. But there are a couple of approaches. The first approach is going to involve another mirror and mounting another mirror on a PZT, and it will work, but I don't like it very well. And then the next technique is some way we're going to use some polarization techniques to do the phase shifting. So let's look at the first approach. The approach I don't like too much, but it works. So here's our Scatterplate Interferometer, and here's the mirror we're testing. And for convenience, I'll say the mirror has a hole in the center, central obscuration. And I'm simply going to put another mirror there, mounted on a PZT. And this light's going to come to focus on that mirror. So that's the direct beam. It's going to come focus on the mirror and come back. And what was scattered the first time will, come out here. And so I'm going to phase shift the direct scattered beam by moving the mirror a little bit. And if you don't have a hole in the center of the mirror, if the mirror doesn't have a central obscuration, I could have put this mirror over here someplace off to the edge as well. Now, this works. I don't like it so much because, well, probably the vibration effects are not quite as good because this is going to be a different mirror, although it's going to be maybe coupled to this mirror. Certainly, the zero-order fringe may not pass through the hot spot anymore. Of course, as I move this back and forth, the fringes are going to move anyway. And you have to align this very closely to get this at just the right location. But anyway, this will work. People have done this. We've done this. Other people have done it. So that's one approach. Another approach, well, I'm going to show I think it's three other approaches using polarization. And the first one here was done by a number of Japanese researchers, of which Honda here spent a year in my laboratory here many years ago. So what we do here, we have a laser with polarized light and a halfway plate just so we can change the direction of polarization. And so what I'm going to do with this little EO cell, so let's say the polarization is at 45 degrees, and I can break that into an X component and a Y component. And with this EO modulator, I can change the difference in the phase between the X and the Y components. So these beams come down here, and we have our scatter plate. And then in the direct beam, I put it in quarter wave plate. And we're going to go through the quarter wave plate twice, so it acts like a half wave plate. And if I put this at the right angle, 45 degrees, it's going to rotate the direction of polarization 90 degrees. And so the X and Y components are switched. And now I put a polarizer out here that picks either the X or the Y. Let's say that X is what I'm saying here. And I can introduce then a phase difference between the direct scattered and a scattered direct simply by applying a voltage to this EO cell. Okay? So, I mean, this works pretty well. You have to put in a quarter wave plate here. And I guess you get a little phase error due to the light going through the quarter wave plate, but we can compensate for that. Yes?
So the laser is polarized?
So the laser is polarized, and, you know, I put in a half wave plate here to change the direction of linear polarization, change the angle. And so let's put it at 45 degrees for the heck of it. So I have an X component and a Y component. And this EO cell changes the phase difference between the X and Y. Then I come down here, and the scattered come back here. So the scattered direct, fine. The direct scattered goes through a quarter wave plate twice, and we can rotate it. I mean, it's set so it will switch the X and Y polarizations. And then this comes back here and is scattered. And so let's say I pick this polarizer here to pass the X component. So what was X originally in the scattered direct beam is still X. And what was Y originally in the direct scattered beam now becomes X. And so that's how I got the phase difference. Now maybe, I mean, I used to, since I worry about everything, I guess, I used to worry that the scattering of the light would change the state of polarization. But it doesn't do very much. It doesn't change it much at all. It doesn't create a problem. Okay, any questions on how this works? This is one of, I think, 3 techniques I'm going to show. A second technique here, I mean, it's going to be pretty similar, actually. Laser beam polarized, quarter wave plate. So we have circular polarization. Light goes here. And, you know, we don't do anything to the scattered light. It comes back directly through. The direct beam, once again, we send it through a quarter wave plate twice. And so if the light was originally right-handed circular polarization, after going through this quarter wave plate twice, it becomes left-handed circular. And so the direct scattered beam is going to be left-handed circular, while the scattered direct beam was right-handed circular. And we don't see any interference because they have orthogonal polarization. We put in an analyzer here. Now we see interference. And as we saw earlier in the course, you know, left-handed, right-handed through an analyzer, get interference. And the phase of this interference pattern depends upon the orientation of this analyzer here. And if we rotate the analyzer an angle alpha, we change the phase difference between the 2 beams by 2 alpha. So it's sort of the same as the previous slide, except we just have a different way of doing the phase shifting here. So this was published by a couple of people. I think both of them from Poland. Certainly the first one, Potarski, is from Poland. And he's a very, very clever guy. He reminds me a little bit of Shaq. I've only met him a couple of times, but I think he's a little bit like Shaq, both very clever and just knows everything. And so whenever you see his name publishing a paper, you should read the paper. Probably pretty neat. The third technique is something that a student of mine, an idea one student of mine came up with, Jay Van Delden, and then the other student, Michael North Morris, who I mentioned before, had made these computer-generated scatter plates. He actually did this for his dissertation. So I think this is a very clever idea. I won't say it worked extremely well, but it's a pretty clever idea. And the idea is the following. We're going to make our scatter plate out of a birefringent material, say calcite, for example. And so the refractive index that the light sees when it goes in this calcite depends on the direction of the polarization. So S and P components will see different refractive index. Okay? So I'm going to make a scatter plate, and we'll look at slides for doing this in a second, but I'm going to make a scatter plate by etching into this surface. Then I'm going to put a glass slide on here with some index matching fluid in here. So this calcite has two refractive indices depending on the direction of polarization. And so I'm going to make this index matching fluid have this refractive index of one of these two refractive indices of this calcite. And so when I illuminate this with, say, S component polarization, the light will scatter. But when I illuminate it with P, say, these height variations are index matched out, and the light will not be scattered. So this will scatter one state of polarization, but not the orthogonal state. So when Jay Van Delden told me this, I thought, boy, I think that's a really clever idea. I like that. So we had to do it. So do you understand what we're doing here? What we're attempting to do anyway? And we will do it. We'll make it work.
So one polarization scatters and the other doesn't?
The other one doesn't because these little height variations are indexed matched out with this fluid, and so it doesn't see any roughness here.
So that makes sense, but now I'm thinking you have two polarizations going through the scatter plate, and then on the return that same...
Oh, we'll worry about that in a minute. Let's just go through it once now, and then in a minute we'll worry about when we return. But if I just go through it once here, you'll see that one state of polarization will scatter, and the other one won't. Well, first, now we have to make this thing. And so, I mean, this is what we talked about before. We take a substrate, we put some photoresist on it, we expose this either using laser speckles, or we're going to use a mask that was made using a computer, and I'll show a slide of that in a second. Well, I'll show it right now, and then I'll come back here. So we could make a mask that was made with our electron beam recorder. So this is our computer-generated, right here is our computer-generated speckle pattern. And so we will expose this, and expose our photoresist. And then we will develop it. And then we will etch it. So we etch right into the calcite. And then I'll strip off the photoresist. So we end up with a piece of calcite here with regions that are etched away. And so that's what we have right here. Okay, any questions? And then we'll make our interferometer in a second. And we'll worry about what happens when the light goes back through the scatter plate the second time. Okay, so here's our scatter plate interferometer. And today I added a reference here. If you downloaded your notes before about 12:30 today, which you probably did, you don't have this reference, but I just added it so I didn't forget it. So we're going to use a laser source I don't know why, but we do. We don't have to. And we're going to focus the light on a piece of ground glass. And, you know, and we can vary this focal position to vary the size of the source, too, which is nice. Anyway, we'll rotate this so we don't get speckled. A lot of ways we can do the phase shifting here. And why we picked this particular one, I think, was because we happen to have a liquid crystal retarder. So we put in a polarizer here. So light's polarized at 45 degrees. And so I can break that into an X component and a Y component. And we put this little liquid crystal retarder that when we apply a voltage to that, we will change the phase of, say, the X component here relative to the Y component. So that's one way of doing phase shifting, and that's what Michael did. So now we come down here. Here's our scatter plate, and that's our scatter plate, with the calcite index matching oil and a glass slide, cover slide on it. And now to get around maybe the problem you were thinking of a little while ago, we're going to put a quarter wave plate in here. So let's say the S component is scattered here. P component's not. So we have the direct beam coming down here, and the S component is scattered out here. Going through this quarter wave plate twice, we switch the S and the P. And so if what was originally S was scattered the first time through, when we come back, what was originally S is now P, and it will be not be scattered. What was P will now be S, and it will be scattered. And then come over here and we'll put in our analyzer at 45 degrees, and we'll have our interference pattern. And by changing the voltage to this liquid crystal, we can change the phase difference between S and P components. So the beam that was scattered the first time will not be scattered when it comes back, and the beam that was not scattered the first time will be scattered when it comes back. And so we have what we want.
Better efficiency with your light then also?
Better efficiency? Well, yeah, we should. I don't know. The results, the hot spot's going to be pretty bright for some reason here. But you're right. We should get better efficiency this way. I mean, this is it was hard to implement, I guess I would say. It works. I'll show you some results in a minute. But the idea I thought was so brilliant when Jay told it to me that it ended up being harder to actually implement than that. So if we come here, well, I don't know, this doesn't show anything, but there's a light source and a beam splitter and a scatter plate and a camera and stuff, but can't really see it from the picture. But here are our 4 phase shifted frames. And lo and behold, I mean, I say that in a normal scatterplate interferometer, of course, the zero order fringe goes through the hot spot, but when you do the phase shifting, of course, that's not true anymore. I mean, that's the whole purpose of it. And it worked. I mean, the hot spot is brighter than I ever wanted, but it worked fine. And we were able to take good data. This was for testing a mirror. This mirror did not have a hole in the center, but the bright spot was so bright, we masked it out, and so you don't see the bright spot. And then we tested the same mirror using a regular phase shifting laser-based Fizeau interferometer. Well, I got pretty good results. So, I mean, it worked. It was a struggle in some ways to get it to work. It wasn't a struggle for me because I didn't have to do anything, but Michael had to get it to work, and it was a little struggle. But he got some pretty good results using it. Any questions? No? Well, I have one more slide on a scatterplate interferometer. But I don't really, I have about 4 minutes left. I don't really have time to give it justice. The one last slide. It's a different type of scatterplate interferometer. It's kind of cool, actually. So I think I'll wait until next class to do that. So any questions before we break? Okay, well, thank you for coming, and I'll see you next class.